Hi dear students, exercise 5.8 is based on two theorems. So very first thing which you have to remember, that is you should know about these two theorems, then only you can solve that exercise 5.8. So I have written both the theorems here. First one, Rolle's theorem. You have to remember its statement first. Let f from closed interval ab to r, means there will be a closed interval given to you along with the definition of a function. Then you have to check that function from closed interval to real numbers, means any kind of output it may give, be continues on that closed interval or not. Then and differentiable on open interval ab, means it should have its derivative on open interval, means a and b are not included except ab. In between what are the numbers, you have to check, okay, your function is differentiable on these numbers or not, such that fa equal to fb. After that you have to check answer of that function on a and on b, are they equal or not, and if they are equal you are able to write them. You can say ab are some real numbers, ab are also from real numbers, but you are able to write c. Then there exists some c in open interval ab, means there will be one number in between a and b in the open interval on which it was differentiable, such that derivative of your given function or statement at that number c will be equal to 0. So students, remember this definition of theorem. It may come for 1 mark in examination also, so remember it. Then they made our work more simple by giving one more theorem. See, that theorem is mean value theorem. We can say it as Lagrange's mean value theorem, or mean value theorem we write as MVT, mean value theorem. So same definition almost. Let f from closed interval ab to r be continuous. Same line. Then and differentiable. See, differentiable on open interval ab, same line, but they removed this condition fa equal to fb. They are writing here then there exists some c belongs to closed interval ab, same line, such that derivative of a function at that point c which lies in open interval ab will be equal to fb minus fa upon b minus a. So students, remember this is also important for 1 mark. There is only little bit change in the derivative. In Rolle's theorem it was at c and we used equal to 0. In this, f dash c equal to fb minus fa over b minus a. So learn these two theorems. Firstly, you should have knowledge of these definitions. Then only you can apply these theorems in exercise number 5.8. We have mainly questions based on these two theorems only. So see what is given next in 5.8 in question number 1. Students, our first question is verify Rolle's theorem for the function given fx equal to x square plus 2x minus 8, and this x belongs to closed interval minus 4 comma 2. Try to remember Rolle's theorem. What was that? I want to repeat that. Rolle's theorem start with f from closed interval ab, two real numbers, continues, then f derivable on open interval, and one more condition, f at a means here you are minus 4, should be equal to f at b, means at 2. So their answer should match. Then there exists a c belongs to open interval ab, such that f dash c equal to 0, means derivative of function at that c will be equal to 0. So we have to use all the 3 steps given in the Rolle's theorem. See how one by one I will write all the details here. So we have given this fx which is equal to x square plus 2x minus 8, and in it is given in, or you can say x belongs to minus 4 2, or you can write in minus 4 comma 2. Let's write as given here. You can mark x belongs to this closed interval. There is no issue. You can mark in also. So we have this. Very first condition, you have to check its continuity. Continuity doesn't mean you have to prove left limit equal to right limit or any other thing. Continuity means you have to check this function is continuous or not on these numbers or in between this interval, closed interval. See, this is a polynomial function, and all the polynomial functions we can say they are continuous. So try to remember, polynomial functions are continuous functions. So we have to write, since fx is a polynomial, so if it is a polynomial, therefore fx is continuous. And where it is continuous? In the closed interval. What is the closed interval? Minus 4, 2. See students, they are AB actually. They are in the form of closed interval AB. So we proved it is continuous in closed interval minus 4, 2. Now what about its differentiability, or will it be derivable? Polynomials, we can easily derive, means we can easily find their derivatives. So if it is a polynomial, therefore it will be derivable on open interval. So you have to write, therefore fx is or will be derivable on open interval minus 4, 2 also. Okay, so it will be derivable on minus 4 comma 2 open interval. Then what was the condition number 3? Third condition was you have to check f a equal to f b or not. What is a? A is minus 4, b is 2. So we have to write now f at minus 4. Solve this polynomial by putting minus 4 in place of x. Minus 4 square plus 2 into minus 4 minus 8. And answer is minus 4 square 16 minus 8 minus 8, or 16 minus 16 equal to 0. Secondly, f at b means f2. Put 2 in the polynomial. 2 square plus 2 into 2 minus 8. 2 square 4, 2 into 2 4 minus 8, or 8 minus 8. Lastly, answer is 0. So you can write therefore f at minus 4 equal to f at 2, and they both are equal. So we marked 3 conditions: continuity, differentiability, and f equal to fb. So you will write therefore all the conditions of Rolle's theorem are satisfied. So all the conditions of Rolle's theorem are satisfied. So then what will be the last step? Therefore, there exists C in the open interval. Which open interval? In definition you marked AB, but now you have minus 4, 2, such that derivative at that this C of this given statement will be equal to 0. What is derivative of your given function? I'm going to erase it. See what is definition given. It is x square plus 2x minus 8. So you don't have any need to write its derivative separately. So you can write here f dash c equal to 0. What is f dash x? In the rough work you can mark it is 2x plus 2. Derivative of this statement given 2x plus 2. So we will write now c in place of x, because we have to write f dash c equal to 0. I am repeating the same again. So what is derivative? 2x plus 2. So when you replace it by c, you have to replace x by also c. So you have 2c plus 2 equal to 0, or solve it for c and you have to check c belongs to open interval minus 4, 2 or not. So it is 2c equal to minus 2. C equal to minus 2 over 2, or lastly its answer is minus 1. Is it a member of this open interval given minus 4 comma 2? Yes, it lies in this interval. So it lies, therefore this theorem verified for Hence, Rolle's theorem is verified for or at C equal to -1. So this theorem is verified for C equal to -1. This was our question number 1. Try to remember, there is a surety about one question in examination from this 5.8 exercise. Very important work. So try to understand and try to write it once again by yourself. See what is given next. Students, our next question number 2 is, examine if Rolle's theorem is applicable to any of the following functions. Can you say something about the converse of Rolle's theorem from these examples? Means you have to check Rolle's theorem is applicable or not, and after that you have to write about converse of Rolle's theorem also. Will that be possible or not? So very first thing we will start from part number 1. So part 1 is fx equal to greatest integer of x for sum or for x belongs to closed interval 5, 9. Students, here I want to make it very clear. Greatest integer functions on proper values, like on integers 5, here we have 5 to 9 closed interval, 5, 6, 7, 8, 9. All are included. In between there are so many numbers if we think about real numbers. But on these proper values of integers, your greatest integer function will never be continuous. And if it is not continuous, it will not be differentiable also. So you have to remember it for greatest integer function. So I have to write it. Since this, greatest integer function fx is neither continuous nor differentiable or derivable, so not differentiable at x equal to 5, 6, 7, 8, 9. This is a special function which is called greatest integer function, and remember, on proper integers it will never be continuous and differentiable. And one more thing, there are two conditions, continuity, differentiability in Rolle's theorem, they are not fulfilled. Now the third condition is fa and fb. So we have to write fa means, what is a? 5. So you have greatest integer of 5, so that is 5. Then f at 9, you have to write 9 in this big bracket, or greatest integer of 9, that is 9. So you have there this type of relationship. They both are not equal, means f at 5 is not equal to f at 9. They are also not equal. All the three conditions are not applicable. So we can say, therefore Rolle's theorem is not applicable. So if Rolle's theorem is not applicable, direct we mark. Now about converse. See, try to remember one more thing which is very special. Derivative of greatest integer function will be 0. So when you write derivative of a greatest integer function, its derivative will be 0. So we can say, since f dash x, yes, its derivative equal to 0 for all the values or all the points in open interval 5, 9. At every point, because its derivative is 0, so for all the points it will remain the same. Therefore, converse of Rolle's theorem is also not true. So converse is also not true in this case, because derivative, when you write derivative of this greatest integer function, it is 0. Whatsoever you put here in place of x, you will get answer equal to 0. So converse of Rolle's theorem will also be not true here in this case. So this was part number 1. Now we will start part number 2 after this. That is almost similar to this. So I will do changes here in this. See how to mark it. Its definition is same. We have to write here minus 2, comma 2. Then I have to change it first. You have every point between minus 2 and 2, minus 2, minus 1, 0, 1, 2. All are included. So we can say since fx is neither continuous nor differentiable on or at all the integers, proper integers, they start from minus 2, minus 1, 0, 1 and 2. So it is not continuous and differentiable on these integral points. Now what is fa and fb's value? Fa means f of minus 2 or greatest integer of minus 2 will give the same answer minus 2, and f at 2 will give greatest integer of 2 which is 2. They are also not equal. F at minus 2 and f at 2, they are not equal. So Rolle's theorem is not applicable. If Rolle's theorem is not applicable, what about converse? Its again derivative of greatest integer function is 0 for all points in minus 2 and 2 open interval. So converse of Rolle's theorem is not true. So this was part number 2 of this. Students, our third part is fx x square minus 1 given for x belongs to closed interval 1 comma 2. See, this is a polynomial, and you know we discussed in question number 1 polynomial functions are continuous and derivable. So we have to write here since fx is a polynomial, and if it is a polynomial, therefore fx is continuous. Where it is continuous? In a closed interval 1, 2, and fx is derivable or differentiable in open interval 1 comma 2. What is a1 b2? So it is closed interval. Okay, so we have to write it is differentiable or derivable on 1, 2. So two conditions of Rolle's theorem are fulfilled. Now third condition, you have to write fa equal to fb. Check what is fa. A means 1, f at 1, 1 square minus 1. Fill in this definition of fx. 1 in place of x. You have 1 minus 1 equal to 0. Then f at b means f2. It will be 2 square minus 1 or 4 minus 1 equal to 3. Are the same? You have to write f1 not equal to f2. So third condition not fulfilled. So we will say therefore Rolle's theorem is not applicable. So Rolle's theorem is not applicable in this case because of this third condition. It is not true here. So we have to write now converse. What about converse? Try to think. In previous two parts you marked derivative of greatest integer function is 0 for all the points. But this is a polynomial whose derivative you can find. What is derivative of this polynomial f dash x? It is 2x. But Rolle's theorem says there exists a c for which derivative of this statement should be equal to 0. Let's start from f dash c equal to 0 in reverse order. See what is given. So we have to write therefore f dash at c equal to 2c, or we can say f dash c equal to 0 implies 2c equal to 0. Or what about c 0 over 2 or c 0? Is it a member of open interval 1 comma 2? This c should be member of the open interval. You marked in the definition c belongs to open interval a comma b, but this c is not a member of open interval 1 comma 2. C is not a member of this interval. So therefore we can say converse of Rolle's theorem is not true. Converse is also not true in this case. So there were three parts of question number 2. Now we will go further for question number 3 after this. See what is given there in third one. Students, question number 3 is if f from closed interval minus 5 to 5, f from this minus 5 to 5 closed interval to real numbers is differentiable function, and if f dash x does not vanish anywhere, means at any point whatsoever you want to put in derivative, your answer will never be equal to 0. Then prove that f minus 5 not equal to f5. So value of function at minus 5 will not be equal to value of function at 5 in this case. So see its solution. You have here clearly given, since f from this closed interval minus 5 to 5 to real numbers is a differentiable function. So if it is a differentiable function, therefore fx is continuous. For Rolle's theorem to be satisfied, see, to be satisfied, why I am writing it? We write differentiability after continuity. So if it is differentiable, we have to write Rolle's theorem, where verified only that if fx is continuous. So fx is continuous for Rolle's theorem to be satisfied. Then we write one more thing. There exists C in open interval. Which open interval? This minus 5 to 5, such that derivative of your function at c equal to 0. But when we write derivative of function at c equal to 0, if it satisfies this condition, f at minus 5 equal to f at 5, means f at a equal to f at b. But according to question, what is given in the question? In question given, derivative does not vanish anywhere. We can say derivative at c will never be equal to 0. And if you have its opposite, derivative not equal to 0, then here also you have not equal to. So f at minus 1 should also not be equal to f at 5. So f at minus 5 will also be not equal to f at 5, because you have not equal to sign for this. It will also be having the same sign. So we have this as our third question. Little bit confusing to remember, but it need concentration to write and concentration to remember these topics or theorems. So carefully write these things. Try to write it once again by yourself to understand. See what is given next in question number 4. Students, question number 4 is about mean value theorem. They have given verify mean value theorem if fx equal to x square minus 4x minus 3 in the interval AB, closed interval AB, where A1, B4. In other words, we can say our interval is 1, 4, closed interval. So try to remember conditions for mean value theorem. Very first condition, your function should be continuous. Second is it should be derivable. And we write here directly derivative of function at c equal to fb minus fa over b minus a. But the thing is, will it be continuous or derivable or differentiable? See, this function fx is a polynomial. Try to remember polynomials are continuous and differentiable on all real numbers, whether you have in the form of an interval, okay? But they are continuous and differentiable on all the real numbers. So we are going to start it. Given is we have fx x square minus 4x minus 3 in 1, 4. So we will write, since the same wording as we used in question number 1, fx is a polynomial. So if it is a polynomial, therefore fx is continuous. But try to remember how you write continuous in closed interval AB or 1, 4, and fx is derivable or differentiable, meaning is same, in small AB or 1, 4 open interval. Okay, so they are, both the conditions are there. And in advance, because it is about mean value theorem, you can find fa and fb, means f at 1 and f at 4. You can find these values. 1 square, when you put 1 here in place of x in the statement, minus 4 into 1 minus 3 will give 1 minus 4 minus 3 or 1 minus 7 or minus 6. and f at 4. 4 square minus 4 into 4 minus 3. 16 minus 16 minus 3, or you have minus 3 answer. But no need to check they are equal. You don't have any condition like this in mean value theorem. You have to write only therefore there exists C in open interval 1 4 such that derivative of your function means f dash c equal to fb minus fa over b minus a. So by using this only we can check what answer of C is coming, and that C should lie in this open interval. Then only you can say your theorem is verified. So see what answer is coming. What is derivative of your given statement of polynomial f dash x? You can write in the rough work. What is derivative? X gives derivative 2x minus 4. Constant's derivative 0. You know about it. Okay. So I am going to put value. F dash c means 2c minus 4. Replace x by c here. 2c minus 4 equal to what is fb? fb this one minus 3 minus of fa. What is a? 1. So it is minus 6 over b minus a. 4 minus 1. Let's write answer of this. Okay. So I am going to erase these steps. So you have 2c minus 4 equal to minus 3 plus 6 over 3, or 2c minus 4 equal to, here you have 3 over 3 which will give 1, or we can say 2c equal to 1 plus 4. Lastly I am able to say here c is equal to 5 over 2, and 5 over 2 means 2.5. Will it lie in open interval 1 comma 4? 2.5. Yes, it is in this open interval. So your C lies in the open interval AB or 1 comma 4. Therefore mean value theorem is verified for C equal to 2.5 which belongs to 1 comma 4. This was our question number 4. So thanks for watching this. In next video we will start our question number 5 onwards.